This is a semester 2 review, problems 21 to 30. Problem 21 says write an equation of a cosine function with an amplitude of 4 and a period of 3 pi. So the sine and cosine functions have this general format, where A is the amplitude, H is the vertical shift, that means the graph has been moved up or down, K you get from the period, and C you get from the phase shift. And notice I use the word from. So I know we're writing a cosine function, and the amplitude gets substituted in for A. But the thing is, because I don't know what the graph looks like, we put a plus or minus sign in front of the amplitude, because I don't know if that cosine graph starts at a maximum or starts at a minimum. Alright, so next we're going to find, there's no H. Oops, I don't know why I did that. There's no H because there's no vertical shift. There's no phase shift. So the only other thing I need to worry about is what's K. This is the case where we set the period equal to 2 pi over K. This is going to be a proportion, and we solve proportions by cross-multiplying. So 3 pi K is equal to 2 pi. I divide both sides by 3 pi, and the pi's cancel, and I find out the K is 2/3. Now, sometimes we don't use theta, sometimes we use X or T, so it doesn't really matter what input variable the problem is using. And this is the final answer. Problem number 22, write an equation of a sine function with the given amplitude, period, phase shift, and vertical shift. So again, it's the same equation as in the last problem, except instead of cosine, we're going to use sine. When you are substituting in for A, K, C, and H, two of these variables can be substituted in without doing any work. And those two variables are amplitude and vertical shift. So I know that y is equal to plus or minus 2 sine of k theta minus c plus, oh, I forgot to write down the vertical shift. It's -1 plus -1 or -1. At this point in time, you may or may not be able to figure out which multiple choice answer is the right one. So you may have to do a little bit more work. Like in the last problem, the next thing you find is K. You find that by setting 2 pi over K equal to the period. You can cross-multiply this proportion, however, you may be able to figure out real fast that K is 1. So I'm going to get rid of this, and I don't really need to put a 1 there because it's implied. But you need to find K in order to find the phase shift. We set C over K equal to the phase shift, which was pi. You replace K, since we know what that is. So I'm going to erase K here, and we're going to put in 1 for K. And we're going to find out real fast that C is pi. So now I'm going to put pi in here, and there's my equation. Problem 23 wants me to write an equation of an inverse function for y equals sine 4x plus y. Remember, the way that inverses work is you basically flip-flop x and y, and then you solve that new equation for y. So I want you to think about the problem algebraically. In Algebra 1, we would first subtract 1. I can't divide by 4 yet, and the reason I can't divide by 4 is because I'm taking the sine of 4y. So at this point in time, I would get rid of sine by taking the inverse sine of the other side. Now notice that I put the x minus 1 in parentheses. That's because we're taking the inverse sine of the entire quantity, not just the x. Now I'm going to divide everything by 4. So it would be the inverse sine of x minus 1 over 4 is y. In 24, we're going to hit the Chapter 7 problems where we worked with identities. So in problem 24, we're going to verify the identity cosecant squared is equal to cotangent squared plus sine times cosecant. Unfortunately, there are lots of ways of verifying this particular identity. One way is to subtract cotangent from both sides. And then if you look at your Pythagorean identities, you find out that this was just equal to 1. And cosecant is 1 over sine, and sine times 1 over sine is 1. Another way of attacking the problem is to work with the more complicated side. So cotangent squared is the same as cosine squared over sine squared. And we already know that cosecant is 1 over sine. So what ends up happening is we get cosine squared over sine squared plus 1. And then we have this little process for combining fractions with unlike denominators. It looked like cross multiplying. So we get cosine squared plus sine squared over sine squared. And cosine squared plus sine squared is 1. And 1 over sine squared is the same as cosecant squared. So that's another way of attacking the problem. I realized that the first method was a lot shorter, but in order to get it verified that quickly, you need to understand the manipulation of the Pythagorean the Pythagorean identities. Another way of determining or verifying, I should say, an identity is to work on both sides. So in this particular problem, I'm going to start by making secant 1 over cosine. And on the right-hand side, tangent is sine over cosine. Then on the left-hand side, I'm going to do that little multiplying process. So 1 minus cosine squared all over cosine is going to equal sine squared over cosine. And then 1 minus cosine squared is a manipulation of one of the Pythagorean identities. It was equal to sine squared. And as soon as both sides of the equal sign are equivalent, you have verified the identity. Number 26 asks you to simplify the expression into one trig function. However, you can't convert cosines and sines. It turns out that this is the same as the double angle for cosine, so I'm not sure if that was the intention of the problem. Number 28 also wants me to simplify the expression into one trig function. Since the denominators are not the same, we're going to do our little multiplying process. So I get 1 plus sine theta plus 1 minus sine theta all over. Now this is interesting. I'm going to skip work because this is in the form a minus ba plus b. Whenever you have that product of a sum and difference, when you multiply them, you get a squared minus b squared. So I'm going to get 1 minus sine squared. Now in the numerator, these cancel. So you're left with 2 over, and 1 minus sine squared is the same as cosine squared. And anything over cosine squared is the same as secant squared. Apparently there's no 28, but there is a 29. So 1 plus tangent squared theta over tangent squared theta is equal to cosecant squared theta. Now I know some of you are looking at the problem going, I want to cancel those. If you do, you kill a kitten, and we don't want to kill the kitten. So we're going to take that away. Now if you go look at your Pythagorean identities, you'll find out that 1 plus tangent squared is secant squared. And then secant squared is 1 over cosine squared. Tangent squared is sine squared over cosine squared. When you have a fraction within a fraction, you take the fraction in the numerator and multiply it by the reciprocal of the one in the denominator. These end up going away, so you're left with 1 over sine squared, and 1 over sine squared is cosecant squared. Identity verified. In number 30, we want to find the rectangular coordinate for the polar coordinate for negative pi over 5. Now I said that you probably like it better if you change these radians back into degrees. You change radians into degrees by multiplying by 180 over pi. The pi's go away, and negative 180 divided by 5 is negative 36 degrees. Remember in polar coordinates, the first coordinate is r, it's like the radius, and the second coordinate is the angle at which that radius is. We have this formula for finding the rectangular coordinates. X is r cosine theta, and y is r sine theta. So to find the rectangular coordinates, we're going to do 4 times the cosine of negative 36, and we're going to do 4 times the sine of negative 36. And it's okay that the answers are decimals. It's going to be 3.24 for x and negative 2.35 for y. Now remember, if you ask yourself at the beginning of the problem, what quadrant would 4 negative pi over 5 be in? It will be in quadrant 4 because the angle's in quadrant 4 and the radius is positive, so it stays there. Is this ordered pair in quadrant 4? Absolutely. When x is positive and y is negative, you're in quadrant 4. And that's problems 21 to 30 on the second semester review.